Hydrogen is the lightest gas in the universe. Its discovery by Henry Cavendish in 1766 caused an unbelievable sensation. People had never ever seen that you could float something like this. You could take they used animal bladders in those days, but you could take a balloon. I've now got rubber balloons, which we have now got today, and you can fill them with this wonderful gas, and up they go. And the sensation was so great that when Henry Cavendish, who was the first person who defined this gas, hydrogen had been known since the Middle Ages, but people simply called it an inflammable, smelly air. That's how they used to describe it. But today, you see, it is certainly very flammable, and it certainly burns, as you will see. But above all, its use as a lifting agent has been historically a sensation, which I'll talk a little bit about here. And you see, I have a balloon here, which is suspended in air. It's almost exactly in a condition as we call static equilibrium. It's going up a little bit, and I can have a tiny little bit of blue tack, and the point is you have to keep adjusting the weight because there is the hydrogen continuously escapes from the balloon. And there you see it's almost perfectly static. Now we have a beautiful airship you see here, and this was one of the great uses of hydrogen when it was first discovered. Could we just do a little round, please, with the airship and gently take her back to the hangar you see? It's radio controlled, of course. We have wonderful facilities for doing this sort of stuff at long range, you see, and there it is beautifully floating in air. So wonderful was the invention of hydrogen, the discovery of hydrogen, and its application for filling balloons that people used to do anything they could to fly. And flying high above the sky was one of the greatest ambitions and challenges. But what I wanted to tell you about, and when people flew, by the way, in air balloons, not only did they do this for pleasure, but they also did it to take measurements of the atmosphere at various heights, the pressure of the atmosphere, how much water vapor there is. They measured the composition of the atmosphere to see whether the air high up was made up of the same gases as the air low down, and so forth. And they used it for traveling. There was a whole wide range of applications for over 100 years, about 130, as I will shortly explain. Can we just have the next slide, please? Because on the next slide, you will see this is the final stage which we reached, was the great airships, by means of which you could travel across the Atlantic. They were filled with hydrogen. It was a luxury way of traveling. About 80 people could travel. It took about 2 or 3 days because the journey was long, but it was a magnificent way of experiencing traveling in a silent way, floating through the clouds. Unfortunately, all of that, as I'm sure you know, disastrously came to an end in 1937, I believe. And can we see the next photograph, which should show you Could I have the next slide? There you are. And this is, of course, the famous disaster when the airship, called the Zeppelin, it caught fire. No one to this day knows exactly why it caught fire. There are all sorts of theories about this. But the honest truth is that one event brought about the end of airship traveling. And that's, as I say, this was in 1930. I believe in 1937, the Hindenburg disaster as it was known. But let's go back a little bit in time. Can we just have the next slide, please? And there is the man who discovered hydrogen. Now you may say, well, how did someone discover hydrogen? Was he sort of pottering around? His name was Henry Cavendish. He was a brilliant scientist, a physicist, a chemist. He was interested in everything about nature around him and a brilliant experimenter. He was extremely shy. He never posed for any photograph, any pictures to be made of him. And this portrait of him is the only portrait that exists, and it was taken because the artist hid behind the curtain and as Henry Cavendish walked by at a meeting, the artist quickly sketched the outline, and so there we have the man. But you may say, well, how did he discover hydrogen? Was he just sort of messing around with chemicals? Was he just pouring acids around? No, you see, at the end of the 18th century, the big topic then that was being studied or investigated were several topics, but one of them was the idea of the concept of a gas. We today, we know there are gases. We've heard that word since our early days, but gases were identified as individual substances with their own chemical and physical characteristics. And the fact that air is a mixture, that is probably one of the greatest discoveries of science of all time, because for thousands of years, people didn't recognize the fact that air is today, we know, a mixture of nitrogen, oxygen, and so forth. And when gases were identified, and they were simply called different kinds of air. So hydrogen was described as inflammable air, air which burns. And that's how Henry Cavendish described it. Can we have the next slide, please? The next slide, you see, the next slide should show, that is a balloon being filled with hydrogen. Well, I am going to show you a chemical reaction here in which we can make hydrogen in the laboratory. Now, I'm going to make the hydrogen in the laboratory by adding dilute sulfuric acid. This is an acid which you meet in schools, formula H2SO4, and I'm pouring it onto a metal. You see, the way that hydrogen was produced historically was by reacting various metals with acids. Acids have been known since the dawn of humanity, as I will explain later, and metals have also been known for many, many thousands of years. And what I've taken here is sulfuric acid, which has been known since the Middle Ages, and the zinc, which was actually discovered in about 1740, but they used to use iron filings in those days. But I'm using zinc today, and the reason is it's more reactive and it reacts more rapidly. So what we have here is what we call a flat-bottom flask. This is a thistle funnel, and I poured my acid in. Zinc is in there with a little bit of copper sulfate acting as a catalyst. And we now have a gas jar. And you see this beautiful gas jar here, which is filling. This type of apparatus was, by the way, was used extensively by the brilliant English chemist Joseph Priestley. It's called pneumatic chemistry. He used the displacement of water by a gas, and he was able to collect the gases there. Now, I'm going to shortly show you that hydrogen is a flammable gas. And during the course of the lecture today, I shall be showing you how hydrogen is also explosive. So I'm going to place my candle here. You see that the flask is filling with, the gas jar is filling with a colorless gas, because that's the way it is described. And there are many, many colorless gases, of which nitrogen and oxygen found in air are examples. But you see, when this now will fill with hydrogen, I will now take off this, by the way, this is called a beehive shelf, that orange thing there, and it has a hole in it. And I'm now going to take the jar off, you see, place a lid on it like that, and then I shall take it off and put another jar on. Now, I'm going to show you something very special. I'm going to set this on fire, and this is almost pure hydrogen. I want you to listen carefully, because it does not make a loud bang. It burns with what we call a thud. Please listen. Nothing special, you see. But I am now going to show you something quite different. You see this jar here? It's only half full. It's only half full. I am now going to let the water out. Look. There it's gone. And what's gone instead of the water is air. We now have a mixture of air and hydrogen. Please observe how this burns. It is rather quite different. And you see, that was a squeaky pop. Now that, you see, is a much more rapid combustion. That's a much more rapid combustion. And indeed, it does a completely different effect. Now, this reaction will continue. I have Andres here. I have, in fact, several helpers. You'll be meeting them this evening. I'm going to ask Andres to kindly remove this apparatus now. Please, at a gentle pace, Andres, while I continue explaining a few important bits and pieces about how hydrogen is made. So, for those of you who are in school, year 9 and above, the typical reaction is acid plus metal makes salt plus hydrogen. As I said, this reaction has been known, but not interpreted that way, for many, many hundreds of years. And Robert Boyle, for instance, also made hydrogen in 1650 or something like that, which was over 100 years earlier, but he didn't understand it in those terms. He simply called it flammable air or inflammable air, and it was very, very smelly because the iron he used was very, 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 very impure, and so the hydrogen had a foul smell. Now, I'm going to just show you that there's another way that we can make hydrogen, but I'm going to do this later because I've just remembered that we ought to move on to a very, very important idea. Andres, could we now fire up this equipment here? While Andres is firing up this equipment, this is quite a complicated experiment. We need to, now there's no water in here, so Andres will bring some freshly boiled water into our boiler, and we're going to explain a few things to you. The fact is that when hydrogen was discovered was a time in the history of science when people were contemplating ultimately what are things made of? What is matter made of? How do substances react? What actually defines a single substance? So hydrogen was defined by the fact that Henry Cavendish measured its density, he measured its combustibility, and he also measured the ratios in which it would explode the most violently when mixed with air. So that was what Henry Cavendish did. But furthermore, Henry Cavendish also noticed, and not only he, that when hydrogen burns, it seems to steam up. It seems to make steam. And that became a very, very big topic for the scientists of the day, is what happens when hydrogen burns. And they thought this is impossible. How was it possible? They didn't call it hydrogen in those days. They simply called it flammable air. And they thought how extraordinary, how is it possible that something can burn and make water? It was very novel ideas. In the history of science, the ideas of how things burn, what happens when things burn, it was very, very difficult to understand. Because you see, when you see a gas burning, or wood burning, or coal, the flame goes into the air, and you don't consider that it's made something different. We now know that. We now know that, you see. And the things disappeared into the air, and people thought that's the way burning happens. And I have to tell you that when it was noticed, and Cavendish and other scientists were very, very keen observers, they noticed that when the hydrogen gas burned, which was incidentally great fun, everyone used to love burning it and making pops and bangs with it because that's what I'll be demonstrating. But they noticed, though, not all of them noticed, that when it burns, it makes a bit of steam, especially if you do it in a vessel where you can collect the vapors. And there, for the first time, was born the idea that perhaps hydrogen is present in water. I'm going to show you an experiment here, which is a remarkable demonstration, in which we actually prove that hydrogen is found in water. As you saw, Andres just poured in some freshly boiled water here. The water is here, it's in this canister here, and we have a burner here which will shortly make this water boil. It will take a few minutes, as I said, but I've got to explain things as I go along. Once this water is boiling, we are then going to pass it over iron, which is in here. Red hot iron. It'll be heated up with burners to a very, very high temperature, and after that, it's reacted with the iron, it'll end up, a gas will come out of here. And that gas, I hope to demonstrate to you, is the gas which we call hydrogen. Now, while we're waiting for that to boil up, I just wanted to explain to you about this splendid illustration of a balloon being filled with hydrogen. You see, filling a balloon with hydrogen, we can do this very easily today. You simply say you get your hydrogen cylinder, or you can make some in a chemical reaction. But if you want to fill a balloon with hydrogen to make it fly, that's an enormous undertaking, and it required whole teams of people. And what I wanted to say is that the balloon which you see there being filled with hydrogen, that, by the way, that picture is taken from a school science textbook which was published in 1857. And you see the enormous scale of it. It had a diameter of about 8 meters, and it required half a ton of iron filings reacting with a quarter of a ton of sulfuric acid. And the sulfuric acid was contained in those barrels which were lined with lead. It was a very, very smelly operation, but people did, and the balloon was made out of rubberized silk, and it was tied down with ropes, and it took 3 days to fill the balloon. So this was an amazing challenge. This wasn't easy just to go out and say, oh, let's fill a balloon with hydrogen. And that's the way it worked. And these balloons became very popular. There's a man called Charles Green. His name was Charles Green. Throughout his lifetime, from about 1780 to 1860, he made 1,200 balloon flights. That gives you an idea of the excitement which flying by balloons gave to people. Now, we're back to the subject now of what happens when hydrogen burns. Is it possible that hydrogen makes water? And as I repeat, when people used to use hydrogen in those days, they didn't call it hydrogen, they called it flammable air, and that was the only way they described it. And I'm going to show you now this boiler. Can you see this tube here? This is what we call a pressure tube. I'm now going to put, it's a pressure relief valve, should I say. If I squeeze this tube now, and it's very shortly steam will come out. Can you see the steam? That means the water's boiling. If I squeeze it so that the steam can't come out, you should see the tube, the level. Can you see that? You see, that's my safety valve. And this is what wherever you have steam boilers, you must have a safety valve. Now, dear Andres, we need to get this to red heat, please. So Andres is now going to heat this. Now we're going to know, we start passing it once it's red hot. We have just rehearsed this literally once or twice. These, by the way, these experiments used to be popularly demonstrated, and now they're quite difficult to do. And what I'm going to say is Andres is now going to use a blowtorch, in fact, 2 blowtorches. That tube is full of iron nails. It's full of iron nails, and we're going to get them to red heat. Once the iron nails are red hot, then we will pass the steam over. Now, this experiment was famously done by a brilliant French scientist, Antoine Laurent Lavoisier, because Lavoisier was doing this experiment to see whether you could actually start with water and make hydrogen. Now, when he did that, he had proved a very important point, and that is the fact that this gas, which we call inflammable gas, is actually present in water. You all know today that the formula for water is H2O, but you try finding that out and proving it. That's what Lavoisier and scientists of his day used to do. Now, this experiment, Lavoisier first did this experiment in a gun barrel, an iron gun barrel, and that's why it's popularly known as the gun barrel experiment. The gun barrel was made of steam, and now you see the iron is now beginning to become red hot. So I am now very carefully, please excuse me, Andres, I just need to come round. I am now going to connect this up, and steam is coming out here quite rapidly. I have to be very careful not to burn myself. And now we connect this up. So now what we've got is steam is beginning to go over the red hot iron. Now shortly you will see bubbles, and here they are. You must excuse me, I'm just going to put another gauntlet on. As you can imagine, this is all very hot indeed. And I'm going to just put another gauntlet on and put this over here. So what I'm hoping to demonstrate for you, you can, by the way, see a little bit of a leak here, but that's okay. We can manage that. Remember, these experiments, the high temperatures which are required for these experiments, they do a lot of damage to apparatus, and cork usually burns. I'm just going to put this in a little more firmly. Now just do it a little more firmly, and you see this bubbling here. Now, if we can show that this is hydrogen, then that will have shown to you chemically that the water contains hydrogen inside it. But then you see, what's happening to our iron nails? That's the question. The iron nails were inside. We'll have a look at those afterwards. But what you will see is the iron nails, they change color. They go from a nice silvery color, which you see was our steel tube. It's a steel tube which is basically iron. But when they've reacted with the water vapor, the steam, at that very high temperature there, we've got a temperature there of about 600 degrees centigrade. It's bright red heat. Then those iron nails are no longer shiny. They will have a black color. And that black color, dear children, is iron oxide. It's an oxide of iron because the iron decomposes water into hydrogen, and the oxygen combines with the iron to make iron oxide. Now, we're having a wonderful result here. This is going extremely well. Thank you very much, Andres. And you see the huge amount of heat energy that's being supplied. We will shortly, I'm going to take this one off now, and I shall shortly ignite it. But we'll wait for just a second, and we'll do the other one. And Andres, once this has filled up to about a quarter or a half, I will ask you to kindly switch off everything and disconnect the apparatus, and then we'll want to tip out the nails once it's cooled down to show everyone the nails which were placed inside. The whole tube is full of nails, by the way, and we have to make sure that those nails, and you'll see the ones in the middle, because the whole tube is full of them, will have turned black. Now, Andres, that's brilliant. If you could kindly turn off the burners now, and the boiler as well, disconnect the apparatus. Now, allow me quickly to show you, disconnect it. Yeah, first of all, just very carefully. Thank you so much indeed. You have to disconnect the tube. That's right. Now, allow me to show you once again. Hopefully, you will see that this hydrogen here will burn with a quiet flame, with a very quiet flame. As we did, it should be pretty pure hydrogen. And we listen. There you see, very pure flame. This one, though, I'm going to do my favorite trick, and that's empty the water out, and we now have a mixture of hydrogen and air. Now, with a bit of luck, this will now make a squeaky pop. So I'm going to now take this off, you see. Listen carefully. And once again, you see. And once again, a splendid demonstration. Now, why is that happening, and why is that difference occurring? I'll explain that later on. But now I just wanted to show you a more modern technique for making hydrogen, which we can make very rapidly indeed, using a metal, of course. And this metal will also break the water down, but it's quite a bit more spectacular. And for this purpose, I'm going to ask for the light to be turned off, but not just yet. But not just yet. Allow me to explain. In this container here, I have the metal calcium. Calcium is a very reactive metal, and it was discovered at the Royal Institution by the great chemist Humphrey Davy, by the process of electrolysis, which I'm not going to go into. And calcium reacts with water, because it's a very reactive metal. It's called an alkaline earth metal, and it reacts with water very vigorously indeed. And what I'm going to do, that'll be fine, Andres, what I'm going to do is to sprinkle some calcium granules into this water, and you'll notice they will start bubbling. And as they bubble, they react with the water to decompose it, to release hydrogen gas. Here it was red-hot iron, here we're going to have cold calcium. And as I now sprinkle, I'm going to sprinkle in quite a few drops, quite a few pieces, et voila. And now notice the bubbling. Now, can I have the lights switched off, please? And I'm going to light the hydrogen. Let's see what happens. And there you see a splendid flame of hydrogen burning on the surface of the water. And it's burning with an orange flame. You see, this is the calcium red brick flame, which we associate with the element calcium, and you'll be seeing more of that later on. So there you see hydrogen released in this, and you notice a lot of steam. This reaction, by the way, is highly exothermic. We could still occasionally light bubbles, but the reaction has essentially finished. So, could we have the lights back on, please? Now, in the meantime, you see, the water has become turbid. It's got a white color to it. There's a white precipitate formed in here, and that is a precipitate of calcium hydroxide. So when the calcium has reacted with the water, it has made calcium hydroxide, which is barely soluble in water, and which is, as a suspension there, it's strongly alkaline, and it has now, we could show it's alkaline by pouring in a little universal indicator. For those of you you'll notice that this will turn a very beautiful purple color, a lilac color. There's universal indicator, you see, and that's demonstrating the alkalinity of the water. So just to show that it's a solution of, it's a saturated solution of calcium hydroxide in water. Andres is now tipping out the nails. It might take a little time, Andres, and please take care because they're still extremely hot. Now, can I have the next slide, please? Because I'm wondering whether what it is. It's always, you know, when I set these slides, I don't know what the next one is. I have an approximate. This is exactly what I wanted. This is exactly what I wanted. You see, I have to tell you that a couple of weeks ago, I walked into my bedroom and I noticed there was a magnificent fragrance. There was a magnificent fragrance. And I thought, And I asked my wife, I said, have you spilt a bottle of perfume somewhere? And it was there for 2 or 3 days, this fragrance, you see. And I kept it. It really was very nice indeed. And she said, no. She said, I was given a present by one of my colleagues, and it's a diffuser. A diffuser. I said, oh, I know what that is. And here it is. Here it is, dear children. This has a magnificent smell. It has a magnificent smell. I wish you could all smell it, you see. And the reason is it's called a diffuser. I hope you've read what the slide says. Formulated the law of diffusion of gases. So what is diffusion? Now, for a lot of students who find, you know, a lot of students, they will say, well, the diffusion is the random movement of particles in a manner which is independent of external gravitational forces. And during diffusion, particles move from an area of high concentration to an area of low concentration. And that's it. You learn it as a definition and you don't understand it. But it doesn't matter, you see. What I wanted to tell you is that the fact that gases and it has spread out by themselves, this was amazing. People used to ask themselves questions. How is it that I'm standing in the bedroom, there was no movement, a lovely smell. And you know yourself this phenomenon. And you see, people didn't understand that. But at the beginning of the 19th century, people used to understand that matter was made of tiny particles. This was a very, very important advance in science. The matter, we can't see them, but we know they are there. And John Dalton formulated the atomic theory that particles are made of the tiniest particle of an element is called an atom, which you can't break down any simpler, and so forth. That was 1808. And then they had the idea of atoms joining together in groups of 2 or more to make molecules. And these were very important ideas from the beginning of the 19th century. Now then, they said, okay, so we have atoms and molecules, they're particles. But then they said, how come these particles, they move? They have to move somehow. And that was, you see, and there were 3 states of matter. This is the other very important idea in science at the beginning of the 19th century, is that there are 3 states of matter: solid, liquid, gas. And this became a very useful way of interpreting both chemical changes and physical changes. So in a solid, they understood that the particles were close together and they vibrated. In a liquid, the particles were close together, but they moved with some energy. And in a gas, the particles were spread far apart and they moved rapidly. And this is exactly where this lovely smell comes from. It's for more of the movement. However, and this is the great Thomas Graham, was one of the great Scottish chemists. Thomas Graham said, he noticed that some gases diffused quicker than others. They were already studying at the middle of the 19th century. They were investigating the physics of gases in addition to the chemistry of gases. And it was noted that some gases diffused or moved quickly than other gases. And he started conducting experiments with large numbers of gases and their rates of diffusion. And he discovered that the rate of a diffusion of a gas is inversely proportional to the square root of its density. Now, you don't have to remember that or even try to remember, but in a very, very simple language, light gases diffuse quicker than heavy gases. That is the most basic idea of all. And moreover, why do they diffuse? Why do light gases diffuse more quickly? And we had already then the explanation in terms of movement of molecules, because the molecules move faster. That was the simple explanation which was given then. And then we investigated other factors such as temperature affecting rates of diffusion and so forth. Now, I have a beautiful experiment which I wanted to show you here on diffusion, because you see, as I said at the very beginning, hydrogen is the lightest gas in the universe. Now, if you understood what I just said, we're going to have the second one, over there, but that will be later. Thank you very much there. That'll be okay. Hydrogen, because it's the lightest gas, diffuses faster than any other gas. And there is a splendid experiment which I wanted to demonstrate here, which demonstrates this idea of diffusion and the fact that hydrogen can diffuse faster than the molecules that are made of air. So there are two substances, two gaseous or two aeriform substances. One of them is hydrogen, which is the lightest gas in the universe, which I have in this cylinder here, and the other is air. Now, air is a mixture, and it's very easy to remember. I mean, broadly speaking, if you look at one hand and you say, this is air, 5 fingers of air, 4 of them represent nitrogen, 1 of them represents oxygen. Air is approximately 20% oxygen and 80% hydrogen. And therefore, these molecules, and by the way, the nitrogen and oxygen molecules have a similar density. Hydrogen is much lighter. So, in this experiment here, I'm going to show you 2 experiments. I am going to show you the phenomenon of diffusion and how it can cause pressure changes to occur if one gas diffuses faster than another. Now, what I have here is a device which many of you will recognize. Is called a manometer. And it's a tube which is full of water, colored water on one side, but at the top of the manometer, we have connected here a porous pot. Now, excuse me, I'm just going to show everyone. Now, what do we mean by a porous pot? It's like a flower pot. But the word porous means it allows molecules to flow through it. Molecules can flow through it, and that means you can't literally blow into it and air will come out. But over a period of time, gaseous molecules will flow through this. Not only gaseous, but also liquids. And ions and molecules of liquid. What we're going to do now is I'm going to fill, or Andres will fill this with hydrogen. Once this is filled, and I'm going to do it upside down, you see. Once it's full of hydrogen, we won't know, but we'll guess it's full of hydrogen. I will then, can we do it over here, please, Andres? I will move it over here. I will then place my hydrogen over the porous pot, and very hopefully what will happen is the hydrogen diffusing quicker than air will start pushing the air out in there because it moves quicker. And when it pushes the air out, hopefully it will set up a pressure. So let's try, please, Andres. Yes, much more. Yeah, this needs to have a very, very generous supply of hydrogen. And we can't tell when it's full, but we guess. We just have to use our... Okay, I reckon, keep going, follow me, Andres. Right, thank you very much, that's it. Now, let's watch. Let's see if anything happens. Anything happening? I can't see anything. Has the pressure? And you see, it's forcing the liquid up, you see. And it's forcing the liquid up because the hydrogen is diffusing through the porous pot and it's setting up a pressure. And it's forcing the liquid in the manometer to go up. This is, by the way, just colored water. So we have a splendid demonstration here, you see, of the phenomenon of diffusion. Now, I had an idea, which I had somewhere remember of seeing something about this written somewhere, of using this idea to actually have some fun with it. You know, scientists and teachers like to invent things to have a little entertainment with, and I'm wondering whether any of you can predict what's going to happen here. I'm going to explain to you what I have. I have got three small containers here, which are all porous pots. They have a large surface area. That's the sort of point of the, if you have three, have a larger surface area than one large one. And I have connected this, and now I'm just going to raise this a little. You must excuse me, this has to be very carefully adjusted. This has to be very carefully adjusted for height to a bottle which contains colored water once again, and a little area here where we can build up some pressure, and there is a tube with a nozzle on it at the end. I am now going to repeat the experiment, put the hydrogen, fill this up with hydrogen, and we're going to repeat the phenomenon. It will diffuse. Please, thank you very much, Andres. Let's get this full as much as we can. As much as we can. Okay, turn the pressure down gradually. That's right, that's right, that's right. And now let's see. And you see, a fountain. A diffusion fountain, you see? And this is a remarkable demonstration, once again, of the way that pressure is generated, you see. The gas flows, the hydrogen flows from an area of a rapid movement, of a high energy, molecular movement. The air has less capacity to move because its molecules are heavier, and we have this beautiful fountain. Now, you see, once I've taken it off, then the air gets sucked back in again, so I will just disconnect it there. Now, do you know what? I had thought of this experiment when I was trying to invent sort of interesting effects for everyone. And then I turned to a book which I've got at home. Can we have the next slide, please? This book, the title of the book should be on the next slide, and there it is. And it's a very interesting title, Air and Its Relations to Life, being, with some additions, the substance of a course of lectures delivered in the summer of 1874 at the Royal Institution of Great Britain. This is where we are today, my dear children. And look at one of the experiments which they did. Can we have the next slide, please, dear children? And, dear sir, there it is, exactly the same experiment. So you're seeing an experiment which today you have seen here, a diffusion fountain, exactly demonstrated. By the way, you might be interested to know what this kind of bottle is called with two stoppers in it. It's called a wolf bottle, okay? Today they don't use these, but you see, they have wonderful application, and there is a demonstration of it being used. Now, we're going to, can I just have the next slide? There it is. Thank you so much. That is exactly what I wanted to tell you. I have then now finished the topic. We're going to be going to and forth with a variety of topics, and I finished the topic of the constitution of matter, the idea of particles, molecular movements, motion, and so forth. Thank you very much, Andres. And I have explained to you a little about the three states of matter. This is to do with matter. But now we're going to turn to something rather different. And I'm sure that you know, and this is the concept of light. I'm sure you know that one of the great discoveries in the history of science was Isaac Newton's experiment in 1761 to split white light into the seven colors of the rainbow, the Newton's prism experiment, should I say. Now, I might like to show you that Andres, who's a physics technician, has actually, on the left, you see, you've got like a beautiful diagram. Andres has actually photographed the real living thing. That's what Newton would have seen. Something like that. He took a sun rays from a distant, obviously from the sun, but through a slit in a dark room, and he obtained that rainbow effect, which you see beautifully illustrated on the photo. That's what you get in real life. But you see, this rainbow effect caused a huge amount of interest because people started to say, well, what's light made of? And they had various ideas, and there were two ideas. One of them is light is made of little particles with different colors which all flow together. And the other idea was that light is made of waves. Today we call it electromagnetic radiation. And those ideas persisted for a long time. And I would now like to, I have specially flown over from Milan, is Professor Fabio Parmigiani, who is now going to demonstrate to you something that we humans have known for many, many thousands of years, and it's been used in fireworks. Could we have the lights off, please, or are we ready? Not just yet, not just yet. Fabio, please come in. Now, Fabio has got Ezgi helping him. Ezgi is a student who's very keen on chemistry, and she's one of my assistants. And Fabio, can I hand over to you and ask you to explain what you're going to do?
Thank you very much. We can have maybe the lights down for this, which is going to be a very simple experiment, actually. We're going to light just some solutions of chemicals dissolved in a flammable solvent. You will see here the flame of the match and the light produced by those chemicals. Now, this actually is another sensational experimental fact that is known since very, very many years, from, I would say, maybe thousands of years. If you put different chemicals into a fire, you can get a different color from the flame. But that was actually exploited by two great physicists, by Gustav Kirchhoff and Robert Bunsen, which is the same inventor of the Bunsen burner there, to identify the elements, because by looking at these different types of lights and passing that light to the spectrum, to the prism that Andrew just showed you, you could decompose that light into individual frequencies, into individual wavelengths. And that gave rise to a lot of useful techniques, analytical applications, and ways to identify, to tell the difference between the elements. Because, for example, if you look at these two last flames on my left side and on your right side, they almost look identical to our eye, but actually, indeed, they are different elements, and they would produce a different pattern when you split the light. So this is actually quite beautiful to look at, but also the connection with hydrogen is that physicists and chemists have studied the atomic emission spectrum of hydrogen, and they learned a lot about how atoms work, about quantum physics, and all sorts of different sciences and technologies. Just to let you know, these chemicals are used, or some of these elements are used in fireworks, are used in pyrotechnics, of course, for the beautiful colors that they provide to the flame. And in order, from the right side, you have lithium, which gives a beautiful magenta crimson color, strontium with reddish, more slightly reddish color, calcium with orange, sodium with the beautiful yellow that we recognize from street lamps, barium with the apple green, lime green, boron, beautiful, the deepest green you can get in fireworks still today, copper, bluish green, and then rubidium and potassium, which are very similar in color, almost pinkish purple, and that is what completes the spectrum. We can get colors from different elements, and for many of the other elements, we don't identify exactly by the naked eye the color. But still, these are the most beautiful ones, and I hope this was an enjoyable sight to see how colors are made and what hydrogen led us to discover. Thank you very much.
I'm just going to thank you so much indeed, dear Fabio. I wanted just to show the next couple of slides which reiterate what Fabio said, but also a couple of interesting observations. You see, Isaac Newton did his experiment with the 7 colors of the rainbow in 1761, but people were very interested to look at this rainbow of these colors, and various people started magnifying. They looked at them through very, very carefully. They had optical devices, and they were able to look at these lights, the 7 colors of the rainbow. And a German physicist whose name was Fraunhofer, he discovered that actually there were black lines. There were lines in the spectrum, and he said of the sun, the rainbow, and there you have a solar spectrum that's from the sun, and with these Fraunhofer lines. Now he discovered several hundreds of them, and he noted also their wavelengths, or he made an accurate note of their exactly positions in which they occur. And this became a source of great interest. Where do these lines come from? What actually causes these lines? Well, the answer is they are what are known as parts of the absorption spectrum of elements which are found in the sun. In the vapor of the corona of the sun, elements such as potassium, calcium, sodium, and so forth. And those elements were subsequently, as Fabio said, it was the German chemists and physicists Robert Wilhelm Bunsen and Gustav Kirchhoff who in 1848 invented the technology or the technique of spectroscopy, which is the analysis of colors which are produced by individual elements into discrete lines. Can we have the next spectrum, please? You see here that, as Fabio just told you, two colors which looked identically red. One of them was lithium and one of them was strontium. You saw them. They were at the end of the beautiful flames we saw. But you see, if you analyze those flames and you analyze them and look at the wavelengths of the frequencies, which is what this was representing, we now understand that waves are electromagnetic radiation, then you see they have completely different appearance. And yet, to the eye, they both seem to be red. And that was the remarkable discovery, you see, of this analytical tool. Every single element, if suitably irradiated, will give an emission spectrum of energy levels of the electrons. And this is the next bit I'm coming to, because people said, well, where does this light come from? You heat it up. How come you have these lovely colors? And it wasn't until the end of the 19th century, the beginning of the 20th century, that people started to understand that the atom is actually made up of two particles. Initially, it was just protons in the nucleus, surrounded by electrons, and then Chadwick discovered the neutron in 1932. But they started to understand that hydrogen, being the simplest element, that's the one that it would be worth investigating, because hydrogen had one proton and one electron. And they were wondering what on earth causes these lines when you heat up the hydrogen. Can we have the next slide, please, which shows you a hydrogen atom? That's how, in a simplistic way, we can understand the hydrogen atom, with a proton in the middle and an electron orbiting it. Now, when you heat up hydrogen molecules, of course, hydrogen occurs in a molecular form. When you heat it up, then it starts to emanate a radiation. Could we have the next slide, please? And you see that emanation, it occurred in several series of lines. But I'm just showing you part of the atomic emission spectrum of hydrogen, and you can just see literally a few lines there. And because there was one electron, these lines lent themselves to mathematical analysis, and people were able to relate, and there were several sets of lines which occurred in different parts of the spectrum which were not visible. And by analyzing these lines, a remarkable discovery was made with the spectrum of hydrogen. Could we have the next slide, please? And this, in a very, very simple manner, summarizes the discovery. And it was made by Niels Bohr in 1913. He was a Danish physicist, and he recognized the fact that the electron in the hydrogen atom can only occupy certain energy levels with respect to the nucleus. And it orbits around like the Earth orbits the sun. But then you can, if you energize the nucleus, then the electron can jump up a level. It jumps up to a higher level. And if you energize it more, it will jump up to another level. But, and this was the amazing thing, there was nothing in between. An electron could either be at one level or another level, but not in between. And that was the birth of the science of quantum mechanics. Today, it is thanks to this idea of the fact that electrons in atoms can only occupy certain energy levels that today we have the whole information technology, computers, everything that we have, the mobile phones, anything to do with information technology relies on our understanding of the fact is that electrons in elements can occupy certain energy levels, but not other energy levels. And that idea has been used also to explain chemical bonding, and it's of universal importance. But the point is, hydrogen and the hydrogen spectrum was the element that played the key role in this remarkable discovery. And now, can we just have a look at the periodic classification of elements there? And you see a beautiful periodic, hydrogen is number 1, element number 1, and they have illustrated, you see, hydrogen there, particularly in the middle, in a larger than usual box. But the point of that, of course, is so that people can see what the numbers stand for, and that's not the object. But I thought that this particular version of the periodic table, it would be useful to remind ourselves, because it shows that hydrogen actually is the most widespread element in the universe. Now, that discovery that hydrogen is present in stars, I think something like 78% of the universe is made of hydrogen. And this remarkable discovery was made by a British-American astrophysicist. Her name was Cecilia Gaposchkin-Payne. Cecilia Payne-Gaposchkin, and she was a brilliant astronomer and astrophysicist. And in her PhD thesis, by the way, she went to St. Paul's Girls' School in Hammersmith, not that far from here. And she did her PhD in the United States of America. And in her part of her thesis in 1925, she put forward the idea that hydrogen constitutes the main element in the universe. And that was not very well received. However, subsequent investigations showed, of course, that she was right, and today this is a widely accepted theory of a brilliant British-American lady physicist. So, Cecilia Payne-Gaposchkin, that's her name, and indeed a very notable achievement. Now, I'm now going to go on to something rather different. Can we have the next one? And I wanted to talk a little bit about these balloons and the hydrogen. Now, there is a cartoonish sort of a picture of Michael Faraday, but the honest truth is, you know that we enjoy igniting balloons full of hydrogen. It constitutes the mainstay of interesting chemistry lessons, and it has been constituted the mainstay of chemistry lectures and so forth, because of its hugely entertaining value. Now, you may not know that Michael Faraday, one of the greatest chemists of all time, one of the greatest scientists of all time, who was, of course, founded the children's lectures of the Royal Institution in 1819, and for 40 years he was giving wonderful, wonderful lectures to children, but he invented the rubber balloon. That's the amazing thing. He invented the balloon especially for children's lectures. Now, the first balloon that he made certainly wasn't like today's balloons, which you see behind me. He actually had 2 squares of a thin rubber sheet. He glued them together, and he was able to inflate this with hydrogen, much to everyone's delight. Now, can I have the next slide, please? Hydrogen, of course, I'm coming on to rockets now, you see. And everyone knows that very recently we had this remarkable, the largest ever space rocket constructed, and it's flown to the moon. I think it's on its way back. I'm not sure, I haven't followed the latest, but it's certainly a remarkable achievement. But this is the important point I want you all to know, is that hydrogen is used as a rocket fuel. It's the most powerful fuel imaginable for firing rockets. In its liquid oxygen and liquid hydrogen combined together, they make water. 2H2 plus O2 makes 2H2O. That's the chemical. And the remarkable amount of energy they release is used to propel rockets into outer space. Now, I today am also going to make some rockets. We're going to, together with Fabio and Ezgi, she'll be there, and then we have 2 teams. But before I do the rockets, I wanted just to explain a little bit about hydrogen and the way it explodes. I have 3 balloons here, and they are all filled with something slightly different. This balloon here is filled with pure hydrogen. Now, when pure hydrogen, you see, when I pull it down, it goes up like that, you see. It's very, very buoyant indeed. You saw that at the beginning of the talk. And when you ignite the hydrogen in a balloon like that, it will burn with a dull thud. That's the expression we use. It burns with a dull thud. And that is why, the reason why it burns with a dull thud is because it's surrounded by air. And air only contains 1/5 oxygen. Furthermore, the hydrogen is not actually mixed with the oxygen. It's not pre-mixed. I'm going to ask for the lights to be turned off. This is not a loud bang. As I repeat, it's a dull thud, but it makes a beautiful orange flame as it burns, and you can just see it as I put my flame to it here. So that you see, can we have lights back on, please? Thank you very much. Now, that was hydrogen. I'm in a bit of a hurry. Now, what is that okay, Peter? Yeah. Now, what I've got in this balloon here, is a mixture. Can you see this one doesn't rise so rapidly? This is a mixture of hydrogen and air. So inside the balloon, I blew it up first. I went, and then I added hydrogen to it. So we've now got hydrogen and air, which are pre-mixed. Now, because they are pre-mixed, they will burn much more rapidly, and they will make a bit of a bang. Now, if you're afraid of bangs, the idea is to put your hands over your ears like this, to cover your ears.
We would advise everybody to cover your ears, please.
But I say this is a louder bang. This is a louder bang, but it's still not the ultimate. But I want you to see, not only is there a bang, but there is also a bit of a red flame. Could we have the lights off, please? And you see, thank you very much. Now, can we have lights on, please? Now, you see, I think you will all agree that burnt much more rapidly, but it wasn't exactly, a super, but it was certainly, you could see the presence of the air, which contains 1/5 oxygen. This is the bit I say. Now, in this balloon here, I have a mixture, and you see it's not too rapidly rising, of pure hydrogen and pure oxygen. Now, this is a mixture of hydrogen and oxygen. We don't know whether it's in stoichiometric proportions, but this, by the way, the French philosopher Pilatre de Rosier, he used to call this aria tonante, which in Italian, of course, means thunder air. This makes a very loud bang. Now, once again, hands over ears to make sure that you're not injured. And you'll notice this is a flash. There'll be no nonsense with orange flames here, just a bright flash and a loud bang, and of course a small puff of steam. So let's watch this one. There you are. So that, and did you see, it blew out the flame as well. No, I'm not, listen, any fool can do these experiments. Please, this is the achievements of science. Notice it blew the flame out. Oh dear. Now, what we're going to do now is a demonstration. Can we please, dear children, a demonstration of our own rockets, Now, what I've got here are, these are cardboard canisters, and could be Fabio and Esgi, please line them all up there. Let me explain to you what's going to have we're going to line them up 4 there and 4 there, and we're going to be filling them with hydrogen. Now, these, by the way, can you see these beautiful colors? These rockets, they were all painted by Nathaniel, who's in the audience. I gave him an exercise to do. I said, Nathaniel, I want to have some nice colors to show. So this is what he's come up with. And what I wanted to show you is how this works, because I want you to understand what you're going to see. And what is this? This is a typical canister that's used for Pringles or some sorts of things like that, you see. And there is a plastic lid on it, like this. They all have a plastic lid. And they've got a metal bottom to them. Now, what we're going to do, this is the important bit. This plastic lid has a fairly large hole in the bottom. And the metal top has a very small hole. I'll just expose it to you here. You can see the small hole there. Now, what's going to happen is we are going to fill each of these full of hydrogen. We're going to, put the flame away. Thank you very much. We're going to fill each of these with hydrogen. And when we fill them with hydrogen, you have to fill it right to the brim. And so one of us will be filling, the other will be putting the lid on. And the reason why we've got two teams of people is simply you can do more in a short space of time. And once we fill them, then I'm going to ignite them. And the way we do it is this. We take the bottom one off first, and then we take the top one off immediately, and then we set fire to it. So we've got a team of 4 people. And these, by the way, when we have the flames burning, the flame will burn very quietly. It's pure hydrogen. But this is the clever bit. As the flame burns, so air starts to creep in at the bottom to replace the hydrogen. The hydrogen goes out, it's lighter. And as it goes out, more and more air, until suddenly we have a critical mixture for an explosion. And when that critical mixture for an explosion is reached, there will be an enormously loud bang, and surprising for such a silly little piece of cardboard like this. And then hopefully the cardboard rockets will all take off. And I don't know whether it will happen or not, but I think we should try and spread them out as far as we can. And so before we do this, let me demonstrate the voice nonsense. Let me just demonstrate the voice. Now, have it running. We need quite a brisk speed of hydrogen. Just a second. Before I do this, just one more little demonstration with the physical properties of hydrogen. Hydrogen, being the lightest gas in the air, also can make your vocal cords vibrate differently. Can we have it on now? Now, as I'm talking,
and as more hydrogen goes in, you'll hear that my voice is higher. My voice is higher. Okay, that's the plan. Thank you very much.
My voice was higher because, everyone does this, but it's just a little bit of a demonstration of physics. Now, Andres, so we've got 2 teams of 2 people. I think the hydrogen should be running all the time. And we just simply, are we ready to go then? So have the hydrogen running at high velocity, have it running, and then what you do, keep it running, high velocity. And then as you pull it out, Andres, pull it out the tube, right? And then we're doing the next one. And then we do the next one. Oh, it's already off. Okay, sorry. I can't keep up. The trick is you must fill it, have it right up to the top, then pull it out gently. And as you fill it, then you mustn't get any air in, otherwise it'll explode when you light it, which will be a terrible embarrassment. So we have to keep filling. And I'm sorry, keep filling. Have a high pressure of hydrogen. Speed. I especially brought a full cylinder of hydrogen to make sure this doesn't let us down. Next one, please. Yes, Andres, next one. Yes. Keep going. Is that okay? Are we okay? Yes, please. Getting there? Okay. Next one. Have we done 4? Have you done your one? Have we done all 4? One, I'll do this one. Okay, you do that one. I want you to have the fun. Right, now, the next thing is we're moving these around a little bit now.
Yeah.
We're moving them around a little bit. Take away the hydrogen cylinders. And I do say the bangs occur very suddenly. We want to have them spread out as far apart as we can. Have them spread out as far, so down there around the corner, because what happens is sometimes one sets off and now you want to have one person with a lighted splint, and the other one to remove the things. Now there will be no bang until it takes a while, but then you can start putting your hands over your ears as soon as we've ignited all of them. Do you know what we're doing then, yeah? So I'll show you the first one, and then right, you're gonna. Why don't you use are you sure? No, you do the bottom one first. Always. The bottom one comes off first, off here, then top one off, and now light it. Okay?
Your ears now. Thank you, everybody.
Okay,
And we'll have a surprise.
Off,
There'll be some bangs coming soon.
Okay. Is that a light? I can't. Okay, right. Bottom off here. Yeah, and the top one there. Just chuck away the thing. Okay. Yeah, and now bottom off, top off. Okay, light it. And they're like, right, now we move well away, hands over it. But listen, I'm going to carry on talking because the honest truth is I can't predict these. And while we're waiting for our rockets to take, they do make very loud bangs, by the way. So what's happening is the hydrogen is burning at the top in a very small nozzle. Air is going in through a larger nozzle. And at a critical point, then you'll suddenly hear, I think the flames are all there. I can't see them, but I'm sure they're there. And you'll hear a very loud bang. Now, sometimes they all go off together. Sometimes they go off separately. You really cannot predict this exactly. There's the first one. Now, sometimes they make a bang, sometimes they don't. It's a little bit of luck, but I think you can see the effect and see the lovely colors which are of these miniature rocket. There you are. That one's like that. You know, sometimes, as I say, it's a loud bang. Sometimes it's, but you know, the longer you wait, the louder the bang. Oh dear, that was, so we had a good, so you see, rockets all over the place. Maybe this will be the loudest, who knows? But the point is, I thought with 8 of these, it'll be far more fun. And I'm going to, sorry, let's just wait for that to go. Actually, I'm going to carry on. My dear children, while we're waiting for that one to go off, I wanted to turn to my favorite subject, which is food. And I wanted to, and you might say, well, what on earth has hydrogen got to do with oranges and lemons? Is it possible that one wasn't ignited? Is it possible that it wasn't ignited? Let's look. I'll just carry on. I don't think it'll go off, but you never know. There's sometimes a delayed reaction. But the thing is, we did have some fun. That's the important thing. And I hope you've understood the scientific principles, because it's still burning. It's still burning. That one was still burning. It will go off down there, Fabio. It's still burning. You'll hear a loud bang in a second. Now, could we clear up the debris, please? If you could kindly clear up the debris. I wanted to go on to my favorite topic, which is food. And you may say, well, what on earth has hydrogen got to do with food? Now, I'm sure that everyone likes lemons and oranges, you see. And one of the things, though, which I'm sure you will have noticed, is that lemons and oranges are slightly sour. And you see, and I wanted to tell you, and something that you all know, and I have no doubt you will not dispute, is that lemons are more sour than oranges. Now, the reason why, and acidity, this is to do with acid, what we call acid behavior. The idea of why are things sour is as old as humanity. And this is where hydrogen, as I will explain to you shortly, hydrogen comes in. So lemons are more sour than oranges. We can tell that by taste. But I have in here water with a few drops of this splendid invention of the chemist, and that is universal indicator. And dear Andres, could we move those beakers forward in that sequence? Because I will very shortly, just in the same sequence, because then we could show that. Thank you very much. And I just wanted to show you how we can very easily show that lemons are more acidic than oranges. So if I now take a nice piece of orange here, and I squirt in some orange juice into my universal indicator, you know it's slightly, about that much there, and I give it a little swirl around. Let's see what color it changes. And there you see, you see it's gone orange. Now, for those of you who know a little bit about universal indicator colors, that means that is weakly acidic, you see. But now but you know that in any case, because if I put some lemon juice in, into this one here, and that's roughly the same amount, and give this a little swirl, and you see it's gone red. So this is quite a very interesting way. See, the chemist has invented splendid ways, analytical chemicals, and universal indicator is one of these, which enable us to tell the difference between acids, alkalis, or strength of acids and strength of alkali. And what I wanted to show, I've done a very simple demonstration here, is that I have in these 6 beakers a very tiny amounts of different indicators. The chemists have enabled us to invent all sorts of remarkable substances, and indicators are always great fun because they change color. Now, all of these have a few drops of a different indicator in them, and they've all got a tiny amount of very dilute hydrochloric acid. It's very weakly acidic, just enough to make it go colorless. But in here, in this jar here, I have got the opposite kind of a substance to an acid, and that's called an alkali. And everyone at school learns that acid plus alkali makes salt plus water in a reaction which we call neutralization. And we can detect, if we do a titration experiment, the color will change of the indicator when the solution is exactly neutral. So I'm going to, I've got exactly the same liquid in here, exactly the same, but I've got different indicators. That's the clever bit. And they've all got slightly different colors. And I hope that when I pour in my alkali, that these indicator colors will become apparent. And you see, so there's our first one. And as I pour in, it's the same liquid, but every time we're producing a different color, you see. And that's the remarkable thing about, well, hopefully a different color. Maybe I got, whoops, I've run out. And now I do have, Andres, could you bring me the sodium hydroxide? In the sodium hydroxide, there is a flask of it somewhere. I do apologize. I'm slightly running out of these things. But the point is, these indicators, they have these wonderful different colors. And just for your information, I've got 3 indicators here. Phenolphthalein, which you'll have heard of, thymolphthalein, and paranitrophenol. Thank you so much indeed. So this is less elegant, but it'll do the job, hopefully. Now, let's see what color we get. This, and there you see, and this one we get here, you see. So we have a very nice selection of colors. I'm sorry the green's not too brilliant, but you can see the point. Now, I didn't invent these experiments. There are wonderful chemistry teachers and people who plan experiments to make them interesting, and they have developed such an experiment. So why is it acidic? This is the point. What actually makes acidity? And there were a lot of theories. People wondered, what is it about an acid that makes it acidic? Well, Humphrey Davy in 1817 thought it was just hydrogen gas of some kind. The Lavoisier, the great French chemist, Lavoisier said it was oxygen. In fact, the word oxygen comes from the ancient Greek words oxys and genesis, means the giver of life to acids. In German today, oxygen is called Sauerstoff. Sauerstoff means the sour stuff. So still, the root of that comes of this idea of acidity. Now, the debate ultimately of what actually causes was solved by a great Swedish man, a chemist, and his name was Svante Arrhenius. Can we have the next slide, please? Just very quickly. Now, Svante Arrhenius got the Nobel Prize in 1903. Once again, when he did his PhD thesis, and he suggested that water can split into electrically charged particles. People just thought that was ridiculous. They didn't believe him. They couldn't understand how a neutral particle could split into 2 electrically charged particles. But he was proven to be right. He was proven to be right. That's why he got the Nobel Prize. And today, we understand that water molecules can split into half. Can we just have this? Not 2 identical halves. They can split into hydrogen ions and hydroxide ions. And pure water has equal concentrations, amounts of these, but water with an acid in it has an acidic water, or with a substance which causes acidity, will have a greater concentration of hydrogen ions than hydroxide ions, and vice versa with alkalis. And that was brilliantly, this concentration of the actual concentration was brilliantly interpreted by the Danish chemist Søren Sørensen. Could we have the next slide, please? Søren Sørensen invented the pH scale, and he defined the pH as the logarithm to base 10 of the reciprocal of the hydrogen ion concentration. Now, that's quite a mouthful, but I have found out in the past that if you have friends and you want to impress them at a party how your scientific skills are good, you should say to them, do you know what pH is? And they say, oh, it's that boring thing. I said, no, it's the logarithm to base 10 of the reciprocal of the hydrogen ion concentration. They'll be so dazzled by your scientific expertise that you'll be just around and say, oh, can you tell us more about this wonderful science? So there is the definition. Go and learn it, children. Not only will you score marks on an A-level paper, but you'll also be able to dazzle your friends. Next one, please. And I think now, and there is the pH scale. Those of you who have indicators, and there's the pH 1 to 14. They're all calculated numbers from that formula I gave you, by the way, which is quite remarkable. And those are the indicator, universal indicator. And now can we have the next slide, please? And here we have the final. We're coming to the grand finale. My dear friends, one of the things that are the great honors of coming to the Royal Institution, it's a place with a great tradition. And hydrogen is certainly not the first time that's being debated today. The first time I showed you was the hydrogen diffusion in 1874. In 1910, Sir James Dewar gave a special, he was a brilliant, in the Dewar flask, the vacuum flask, Dewar gave a demonstration of liquid hydrogen, which he was an expert at cryogenics, and he had made liquid hydrogen. There is a wonderful painting of him outside with the apparatus there. And in 1935, the brilliant organic chemist, Professor John Reed, gave a lecture here. It was in November 1935. And the thing about John Reed was that he was not only a chemist, he spoke Somersetian. He gave lectures in Italian, in German. He got his PhD in Zurich. He was a chemist in Australia and did fantastic research on plant materials. One of the most extraordinary characters and a brilliant specialist on alchemy and the history of chemistry. Now, in 1935, and John Reed was also obsessed with exploding hydrogen balloons. Now, he had to find an excuse. He gave a lecture entitled, The Musical Alchemist. It was a Friday evening, I think it was 11th of November, 1935, and the Musical Alchemist, and he decided Michael Meyer was the person in question who composed some canons and fugues for which alchemists used to sing, but John Reed had to find a way of getting music into it somehow because he loved music and poetry and everything. So what he did was he got his the Musical Alchemist. The works were analysed by one of his colleagues at Aberdeen University, and he wrote a special piece was written for a choir to sing while the hydrogen oxygen balloons were exploded. And this is what the words of it are, of the song are. Please, can I have the next slide, please? The words of the song. It was called Hydrogenesis. There it is. Well, I thought to myself, and what he did was he had one of his music colleagues from Aberdeen University to write the song, and he had one of his, and he had the choir. He had a choir from Aberdeen University, which was called the Chemic Choir. Now, I thought it would be wonderful to try and repeat something like that. So I have invited a choir from Highgate School, the Highgate School consort, to come and sing for us today, and the composition, which you're going to hear, has specially been composed by a very, very good friend of mine, former pupil of Highgate School, Dr. Graham Waterhouse. He has specially written music to accompany the explosion of hydrogen balloons. Not 1, 2, but you can count, I've lost track, but there are a large number of them. So, what we're going to do, can I ask the choir, under the directorship of Catherine Harrison, who's the director of our choral music at Highgate School, the choir to align themselves rapidly because time is running out, and I shall be most grateful. And what we're going to do is, if you could line yourselves up, please. I need to get my main prop. I have an important prop here, which I'm going to lift up, and I should have a hammer somewhere. Oh, if I don't have a hammer, doesn't matter, I'll just use this. Oh, look, the nails have fallen out now, so you can come and inspect the nails later. But this will be whoops-a-daisy, please excuse me. You've got Andres, you can do the ignition, okay? You can, I'll tell you when. I'll tell you when you can do the ignition. So listen, where's the candle that's burning? Can we please bring it over here? Esgy, thank you very, very much indeed. So the choir will shortly begin. Now, where is our conductor? Here we are. Now, let's just remind me. So, composer, Dr. Graham Waterhouse, Highgate School consort, Hydrogenesis. Now, David, you're sitting terribly close to that. This is going to make a very loud bang. If anyone is afraid, this is going to be very loud indeed, and I will definitely cover both ears. If you're afraid, if you're not, then you're like a fool, then you're like me, you see. You just simply take what comes. But the thing is, hopefully, I think this one, hang around, I think this one will set off this one. There's a huge amount of preparation went into this, but I very much hope it works. So I do this when they finish this thing, and then Andres will do the thing when they do that, okay? So the moment they've put their hands over their ears, that's when you light it, okay? Well, Hydrogenesis 2022 edition. Thank you so much. Sorry, was that it was. Thank you very, very much indeed.
Ladies and gentlemen,
Thank you very, very much indeed.
a huge round of applause for the fantastic Andrew Szydlo.
Thank you very much indeed, everyone. Come forward, please. Help us. Andres, thank you very much. Thank you very much indeed for your kind attention. Thank you so much. Andres, please come forward. Yes.